Half a century of lunar exploration rests on a few temporary visits and a single set of footprints frozen in the dust. Moving toward a permanent settlement requires a self-sustaining presence, yet the cost of pulling every liter of water and kilogram of oxygen from Earth's gravity remains a massive economic barrier. Artemis bypasses this bottleneck with a new orbital command center, the Lunar Gateway. This spacecraft provides the thrust and communication to manage a continuous presence in deep space, serving as the bridge between Earth and the lunar surface. From this stable orbit, crews can monitor surface robotics and ferry supplies to a fixed, high-value location on the ground. That location is the lunar South Pole, where the unique topography offers a rare combination of near-constant solar energy and accessible resources. But securing the orbit is only the first step. The descent leads to an environment so hostile that survival requires a complete transformation of the lunar soil. At the South Pole, deep basins like Shackleton Crater sit in eternal shadow, where temperatures remain hundreds of degrees below zero. Without an atmosphere to regulate heat or provide pressure, any exposed electronics or biological systems face immediate failure. Beyond the cold, the surface faces a silent bombardment of high-energy cosmic rays and solar particles. Without Earth's magnetic field to deflect them, these rays penetrate standard materials with ease. Even thick-walled inflatable habitats provide insufficient shielding against these solar events, leaving crews vulnerable to radiation sickness. Staying alive on the Moon requires moving beyond Earth-built shelters and finding a way to weaponize the lunar environment against itself. This is the logic of in-situ resource utilization, building a base from what is already there to avoid the prohibitive cost of launching every gram of material from Earth. Precursor missions target the permanently shadowed regions of polar craters, where sun-shielded pockets allow massive deposits of water ice to collect and remain stable for billions of years. While water ice is a vital resource, long-term survival relies on pulling breathable oxygen directly from the dry lunar dirt. Heating regolith to 900 degrees Celsius in chemical reactors breaks the molecular bonds of lunar minerals, releasing pure oxygen gas. The byproduct is a dense mineral slag that, when baked, becomes high-density concrete used to layer habitat modules. Maximizing this protection involves burying the primary living quarters beneath several meters of regolith or lowering the facility directly into the bedrock. These techniques allow the Artemis base camp to be forged from the lunar crust itself, creating a permanent stronghold in the deep south. Inside that armored shell, a pressurized environment must mimic Earth's biological stability. The human metabolic loop requires a constant cycle of oxygen production and waste removal, a process that is currently mechanical and prone to failure. Relying on mechanical scrubbers and water filters requires a heavy inventory of spare parts from Earth, a logistics chain that fails over long durations. Scientists are replacing these machines with living systems, using photobioreactors filled with nutrient-rich algae. Within these green-lit chambers, Limnospira indica algae consume human waste and carbon dioxide to produce breathable air and edible protein. This creates a microscopic piece of Earth's biosphere, safely isolated from the brutal vacuum waiting on the other side of the regolith shielding. By mastering these closed-loop systems, we are proving that the essential components of Earth's biosphere can be transported and maintained anywhere in the cosmos.